And what this algorithm aims to do, right, is to find all the SCCs in a graph of nodes. What is an SCC? It means is that a group of nodes, if it is a strongly connected component, they can all reach each other, right? So here is a really easy example. If we start at this node, we can go here, 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 here. This is another example of a strongly connected component where, let's say we start at this node, we want to go here, 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 and here, right? So we know this is a strongly connected component, that is a strongly connected component, and that is a strongly connected component. Let's say we add a line here to here, right? It connects from that node, and let's say it connects to this one here. This does not make it a strongly connected component because as soon as you cross this boundary, there's no way to get back. And the same thing occurs if we make a node from here to here. Now, if we add a line here, or we add a line back here, these will become strongly connected components because you can go from this node network to this node network, right? So one thing we can kind of gather from this is that we can abstract SCCs, strongly connected components, as a big node, right? Thus, the node network will become a DAG, where it shows the cross-boundary edges, right? On paper, it'll look like this. Note, only cross-boundary edges are shown, right? What is a cross-boundary edge? It's the ones that define one SCC from another. And if we take a step back here and look at it abstractly, let's say you want to describe anything, right? A node network, a map of a country, or even a sphere in a 3D space. How do you describe its boundaries, where it lies? Well, you can describe every single point within it, right? You can describe where the schools are, where a military base is, where the towns reside, right? And that can describe a country. Or you can describe all the areas to which its boundaries lie, right? And this is essentially what we can do here. We can either describe every node that is part of an SCC, or we can describe these as big nodes and simply describe the boundaries, right? And as you can see, the boundaries may be a little easier than describing. So Kosaraju's algorithm aims to show where these cross-boundary edges lie. But the question is, how do we find these cross-boundary edges? How are they defined, right? So here, a naive way to try and approach this is to say, all right, so we have some sort of initial node. From here, we're going to go through every single path. There's every walk within the graph and see if they can somehow get back to our initial node, right? And if it does go to our initial node, then cool, we have a SCC, or it's part of an SCC group, right? And if they don't, then there is either within that node or its intermediates a cross-boundary edge. So this can work. It's going to be extremely slow though, and there's an easier way to do it, which is Kosaraju's algorithm, right? And that is essentially that we're going to reverse all edges in the graph. See, we have this node network, and we're going to reverse the edges, right? Where this guy going this way becomes suddenly this way. Or this guy going this way suddenly becomes this way, right? And we can see here that we have two cases when we reverse a set of nodes. Case one, for each node pair that we have, this guy, this guy, this guy, this guy, this guy, this guy, whichever node pair, if we can go from node A to node B, both before and after the reversal, then it's an SCC. So let's look at this as an example. Let's say 1 and 3, right? This is A and this is B. Before the reversal, we can traverse to B. And after the reversal, we can still revert to B. So we know that these two nodes are part of an SCC, right? But on a high level, we can see that this entire group is an SCC. Now, let's say we have like this guy and this guy, right? A and B. From here, we can go to B, but from here, there's no way to get to B. So these are part of a separate SCC, right? Somewhere between this guy, and this guy allows a cross-boundary edge for two SCCs, right? And of course, case two, if node A and node B was possible before the reversal, but not after, then it's a cross-boundary edge, right? What we just described here. So we can reverse the edges and identify the borders of a strongly connected component. So how do we actually implement this in an algorithm? Well, the first step is depths first search. And we're going to mark the times which each node finish. Right. Next, we will reverse all edges. and then we're going to run depth first search again. And from here, we're going to essentially run it from latest nodes. I'll show you what that means here in a minute. And then after that, we're going to mark our traversals from step 2. And believe it or not, that will get you your cross-boundary edges, right? So let's say we have this node network, right? We're going to run depth first search. Let's start at A. Here, we start at A and we can see that we can go this way, right? This is our first move, going across this edge. From B, we can go to E, we can go to D or F or whatever. Let's say we go to F. From F, we can go to E or H. Let's say we go to H. And from H, we can either go to L or H. We can go to L. Basically, is our only move, right? So we're going to go to 4. Now from L, there's no way to go anywhere, right? So our node has a finishing time of 5. Then we're going to go back 1. H has nowhere else to go. So H has a finishing time of 6. Here we go back. F has another place to go, which is E. So we're going to transfer to that on move 7. Right? We can see E is able to go to L, but L is already done. So E is going to finish with 8. Next, we're going to go back to F and see that there's nowhere else for it to go. So it's going to have the finishing time of 9. Here, we go back to B. We can see B is able to go to E, but it's already done. B can also go to D, which it'll like to do, because this is the only move possible. Next, from B, we have D, and D can go to E, but we already finished. D can go to C, or it can go to K, right? So let's say on move 11, we go to C. C can also go to K, so that'll be our move 12. K has nowhere else to go, so we're going to know it's going to finish at 13. C has nowhere else to go, right? B has already traversed D and all this stuff, so it is going to go and finish at 13. D will finish at 14. E will finish at 15. And A will finish at 16. Okay? Now, our next step. Okay, well, I kind of messed up here. Can I say this is 14? This is 15, 16, 16, 15. Next, we were going to reverse the edges, copy times, and run DFS on the latest nodes, right? The latest node being 17A. When we run it, notice that nothing occurs, right? There's no way to go to B or any other node. So we finish there, and it will be its own SCC. Next, we begin at the next latest node, 14, 15, 13, 16. 16 will be the highest, right? And so from B, we can't go here, 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 but we can go to C. So we're going to bold this line, right? You see it's covered in blue. We bolded it, and then we're at C. Next, we can go to D as well, so we're going to bold that line. From D, we have nowhere else to go, right? Can't go to K, and B's already finished, so this is going to be all placed in a group. Now, what's the next finishing time? Well, it's K at 13, right? And here, we have no arrows to go. This is finished, this is finished, this is inaccessible, so this is going to be its own isolated group. If we keep going along here, we see that 9 is our next latest finishing time, and here it can travel to E, but it cannot go anywhere else, so it will be its own group with F and E. Next is H. We can see that it can only go to L because this is occupied and taken, right? So this will be its own group. And essentially, when you copy traverse steps, right, from this second step, you will essentially get something like this, right? We have this group, this big group, this big group, and notice we copied these bolded edges, right? This is its own isolated group, and we copied this bolded edge, and we copied this bolded edge. Everything you see here, these are the big node here. This is a big node, this is a big node, that is a big node, and that is a big node as well.